How do we look? Good? Is recording? Oh. Hey everybody, welcome back to Quarantine Physics. I had some requests for you guys to meet my dog. So this is my dog, this is Sam. This is our new physics mascot. Today we're going to be talking about methods of charging and conservation of charge. Alright, so continue our discussion about electrostatics. Last lesson we discussed what a charged object is, what it means with the particles inside of that object. We learned that when you have a positive object, you have an object that's missing electrons, because electrons are the only thing that can move from one object to another. So a positive object has a lack of electrons, while a negative object has extra electrons. Something we didn't talk about yet, though, is how do objects actually become charged in the first place? We talked about it very theoretically. Now we're going to dive in and actually figure out how we can put a charge on an object. All right, so the first way that we could charge up an object, we saw this a little bit in the balloon simulation, but you could charge an object simply by friction. This is what happens when you rub your feet on the carpet. This is actually what happens with clouds in the sky. The lightning that's in the sky is the same phenomena as the lightning that goes from your fingertip to your doorknob. It's just on a much bigger scale up in the sky. So this is charging by friction. When we have objects rubbed together, electrons are transferred from one object to another object. In this little animation I have here, we have a PVC pipe and a rag. And when the rag is rubbed on the PVC pipe, as you can see, electrons are going from the rag to the PVC. These objects end up with opposite sign charges because the electrons went from one object to the other object. Notice here that, again, the electrons are the only thing that transfers. The positive charges are left behind in the rag, and the positive charges stay put in the PVC pipe. It's just the electrons that go from one place to another. Now notice here, this is a pretty cool simulation or animation because there's still a few electrons that are left behind. Not every single electron goes from one to the other, but by friction we have a net positive charge here on the left and a net negative charge on the right. There's actually a whole list of objects, objects that more readily give electrons and more readily gain electrons. That's called the triboelectric sequence. Maybe I'll try to get a link in that in our assignment tomorrow. All right, so this is charging by friction. We end up with opposite sign charges. Both objects become charged after the interaction. Okay, we also have charging by conduction. Conduction is our fancy science word for touching. When one object just simply touches another object, how could charges be transferred? So in this case, we have a negatively charged rod, like we could say it's the PVC from before, and then we have like a neutral conductor. And when this negatively charged object comes in and touches this object, the electrons just run over to the other object. No rubbing necessary. They simply touch, and then the electrons dive into this object. And notice here, the very important thing about conduction is both objects end up with the same sign charge. This is a negative object. The electrons run over. Not all of the electrons are going to run. Something that we're going to be learning in future slides is the charges want to run until there's some kind of balance, right? Not all of them is going to go. So this object is going to remain negative, but it's going to be less negative than it was before. And this object gains negative charges. So the electrons run over and both objects end up with a negative charge. That is charging by conduction. All right, next. Oh, I have a little animation to show you. So something that shows up on like the physics regents a lot actually is this device, the electroscope that we talked about before. Now electroscopes can detect the presence of charge, but we could also charge the electroscopes. So the electroscope is neutral, not now, but wait. Okay, the electroscope is neutral. It just detects the presence when it comes nearby, but notice what happens when the object touches the electroscope. It touches, some of the charges run in, and if this is a negatively charged object, the negative charges from this object go to the electroscope, and now the electroscope has a net negative charge, and the leaves separate because there's a bunch of negative charges all over the electroscope, including in these leaves, which makes them want to diverge. But what's the story if this was a positive object that we brought by? Again, the number one thing to keep in mind is like charges repel, opposite charges attract, and electrons move. If you keep those three things in mind, you could always explain what's happening from an electrostatics perspective. If this was a positive object, the electroscope is neutral. And when the positive object touches, now the electrons want to run into the positive object. The electrons leave the electroscope, leaving behind a net positive charge in the electroscope. So if the electroscope's missing electrons, now it has a net positive charge, the leaves have a positive charge, and those two positive leaves are going to want to separate. Again, this is charging by conduction because they simply touch, and then the charges get transferred. All right, next. The third method of charging that I want to discuss is charging by induction. What's cool about this method of charging is there's actually no direct contact between the two objects. So how can this occur? Before we formalize what charging by induction means, we need to talk about this idea of electrical grounding. You might have heard of this term before, like grounding wires or grounding circuits. If you actually take a look at any of the outlets in your house, you have your two live slits, right? And underneath, where it looks like a little face, where the mouth is, that little circle, that's the grounding spot for the plug. And the ground quite literally hooks up to our ground. That's why we call it electrical grounding. So, the electrical ground, there's a wire that literally goes into the earth. And the earth, because it's so gigantic and it's such a good conductor, it acts as an infinite source and an infinite sink of electrons. If there's any kind of surge, we could dump all those extra electrons into the ground. Or if we have a very positive object, we could take electrons out of the ground. And the earth, because it's so massive and there's only, in the perspective of the size of the earth, such a slight change in charge, it stays neutral. So, the Earth is a good conductor and it acts as a reservoir of electrons, which means there's an infinite source. You could get electrons if you need them, or it's an infinite sink. It could take as many electrons as you need if you have a bunch of extra. It neutralizes any object that's connected to the ground by giving electrons if the object is positive, or taking electrons if the object is negative. Okay, so by the way, if you look at any kind of circuit schematic, the ground looks something like this. These lines that kind of get shorter and shorter as we go. So let's explain what this means. We're connected to the ground, an infinite source, infinite sink of electrons. So let's say we hook up a positive object to the ground. A positive object is missing electrons. So if it's missing electrons, if we hook it up to an electrical ground, it could get as many electrons as it needs from the ground, becoming neutral. The electrons will run up from the ground into the object, neutralizing the object. If we have a negative object, we hook up a negative object to the electrical ground. The negative object has a bunch of extra electrons. So by hooking it up to the ground, all of those extra electrons run into the ground until the object is neutral. So the ground is a useful tool for our electrical components. And that's why we have grounds inside of our outlets. So if there's any kind of surge, like I said, those extra charges, whether it's positive or negative, could either run into the ground or run out of the ground to neutralize things and keep our electrical devices safe. Okay, we got what a ground is. You can't answer me. Leave a comment. So here's what the ground is. We need to understand what electrical ground is before we understand what charging by induction means. Okay, so here's the story of charging something by induction. So imagine we have this rod here. This is a material called ebonite, which is easy to charge. We have an ebonite rod and a metal sphere. it's on an insulated stand, that means that all of the charges that are inside of the metal sphere could stay on the sphere and not run into the stand. If we simply bring this negative rod near this object, the object will stay neutral, but notice what happens. Just like we talked about last lesson, the charges polarize. The negative charges in the sphere run away from the rod, leaving behind those positive charges. But here, the sphere is still neutral. Even though the charges are polarized, if we add them all up, there's an equal number of positive and negative charges. But notice what happens here in part B. In image B, this negative rod is nearby, but the metal sphere is hooked up to our ground. So instead of the negative charges running away to the other side of the sphere, now those negative charges have a place to escape to. Those negative charges run away from the ebonite rod, down through the wire here. There's a conducting wire, and it dumps into the ground. Now, if we sever our connection to the ground and pull away our rod, we end up with a net positive charge on our metal sphere. So the story one more time. Neutral sphere, negative object comes in. We connect it to the ground, those negative charges run into the ground. Sever your connection, pull the rod away, you have a positively charged sphere. The objects never made direct contact, and both objects end up with the opposite sign charge in this case. Okay. Now what's the story if I bring in a positive object to our metal sphere? If I bring in a positive object to our metal sphere, the charges will polarize, but in the other direction. The negative charges will get closer to our positive object, and the positives will be left behind. But if we connect it to the ground and we have a positive object here, now the electrons on the ground say, hey, I want to get as close to that positive object as possible. The electrons run up from the ground into our metal sphere. Then we sever our connection, pull away the positive object, and you end up with a negatively charged sphere. Those electrons came out of the ground, and now they live inside of that sphere. That is charging by induction. So, 3 methods. Friction, there's rubbing, electrons transfer from one object to another, end up with opposite sign charge on each object. Conduction, they touch, the electrons run until everything is as equal as possible, and then both objects end up with the same sign charge. And by induction, by hooking up the thing to the ground and bringing a charged object nearby, you end up with 2 objects with the opposite sign charge. Don't memorize these things. Just keep in mind what the core ideas are for electrostatics. Like charges repel, opposites attract, and electrons are the things that move. And if you know those 2 things, you can always tell what's going on with the story of charging by friction, conduction, or induction. Okay, next. So weird. Okay, the next big idea I want to discuss today is this idea of conservation of charge. In class, we discussed the importance of conservation laws. If we, whenever a quantity is conserved, it really helps us better understand how the universe works and help us make predictions in any kind of isolated system. And remember, the entire universe could be considered an isolated system. It depends on where you put your dotted line. So for conservation of charge, in an isolated system where no charges can enter or leave the system, the total amount of the charge in the system must remain constant. A simpler way to say this is charge, electrical charge, cannot be created or destroyed. Big conservation law. This is one of the laws that we still look to today to understand things like that, understand like our frontier physics research. I've talked about the Large Hadron Collider and smashing particles together. One of the things we still look for when we smash these particles together is to make sure the total charge in the system remains conserved. Okay. I don't know, pause the video, write that down. What I want to do now is I want to apply this idea of conservation of charge to make predictions of how much charge might end up on objects if we, let's say, touch them together, charging them by conduction. Very important. All right. So, take a look here. Pause the video, see if you can figure it out, but I'm going to kind of talk through it. Here's the situation. We have two identical metal spheres. That's important. For those of you who might go on to physics studies in the future, if there's anything different about the spheres, then this idea might not hold. But for now, we're going to say everything about the spheres is identical except for the charges on them. This is a 1 Coulomb charge on this sphere. This is a -3 Coulomb charge on this sphere. Remember, coulombs is just a way for us to understand how much charge is on that sphere. It's buckets of charge. So this is 1 Coulomb, positive 1 Coulomb. That means we're missing 1 Coulomb of electrons on this sphere. Here, we have a -3 Coulomb charge. That means we have an excess of 3 coulombs of electrons. 3 buckets of electrons are on this sphere. 1 bucket of electrons is missing from this sphere. So what happens is these metal spheres touch and then they separate. What charge is going to be on each one of these spheres? Okay, when we talked about charging by conduction, we said that the electrons are going to want to run until everything's neutral. And, not neutral, sorry, until everything's balanced. Not only that, but no charge can enter or leave this system based on conservation of charge. So what happens when we charge these things by conduction? So we touch them together, we separate them, and it turns out that each one of these spheres have to have the same amount of charge because the charge will run until it's even. But what value is going to run to each one? Well, if we look, the total charge in the whole system is -3 plus 1, which is -2 coulombs, right? That's the total charge inside of this system. And then we touch it and separate. The total charge in the system has to remain -2 coulombs. But it also runs till it's equal. So what ends up happening is, on each one of these spheres, we have, that's incorrect. Let's see, -2, that should be, I'm gonna fix it. There we go. There should be a -1 Coulomb charge on each one of those spheres. Let me explain. There's -2 coulombs in the entire system. There still has to be -2 coulombs in the system, but this one will have a -1 Coulomb charge. This one will have a -1 Coulomb charge. They run till they're even, and the total charge in the system remains constant. Okay. Bonus question for you. Which way did the charges flow? Did charge flow from this sphere to this sphere, or from this sphere to this sphere? Well, we end up with a -1 Coulomb charge on each one. So this one became negative. This one became less negative, right? Electrons are the only thing that could run from one object to another. So what happens is the extra electrons on this sphere got dumped into this sphere until everything was even. We separate them. The charges, the electrons, came from this sphere to this sphere, and now there's a -1 Coulomb charge on each one of those spheres. Okay? Try another example. So now, in this case, we have a +2 Coulomb charge on this sphere, +3 Coulomb charge on this sphere. Both of these spheres are missing electrons. This one is missing electrons more than this sphere is, because this is more positive than this sphere. We touch them together, we separate. What's the charge on each one of those spheres? It's so weird asking questions to empty room. Okay, what's the charge in each one of these spheres after we touch and separate? Well, the total charge in the system is +3, +2, +5 coulombs in the whole system. Charge can't enter or leave, and it's going to flow until it's balanced. So there's 5 coulombs of charge, +5. They touch, they separate. Flows till it's even, total amount has to stay the same. There is plus 2.5 coulombs of charge on each one of these spheres. Total of 5, split up into 2. Now there's 2.5 coulombs of charge on each. Are we allowed to have half a coulomb of charge? Yes, we are. We can't have half of elementary charges, but if we think of our coulomb as our bucket full of charge, we can have a half full bucket of charge, right? We can't split an electron, but we can have half a coulomb of charge. Okay, again, asking you this question. Which way did the charges go? Did charge go from this sphere to this sphere, or from this sphere to this sphere? Take a second, think about it. Remember, electrons are the only thing that can flow. This one needs electrons more than this one does. So even though they're both positive and both of them want electrons, because this one wants them more, the electrons from this sphere, because remember, there are still electrons here. Yes, it's missing some to give it a positive charge, but there are still electrons on this sphere. There's just a +2 coulomb charge of imbalance here. So the electrons that were on this sphere run over to this sphere, giving them both a net positive charge. This one became more positive, so it lost electrons. This one got closer to being negative, so it gained electrons. All right, let's try another example. Oh man, 3 spheres. Okay, just like I say in class, make sure you can do this stuff on your own. Don't wait for me to give you the answer. Pause the video, try it out, and then play the video, and I'm going to tell you the answer. So, how much charge is in this system? And how much charge do you have to split between, how many objects do you have to split that total charge in between? +4 plus 1 is +5 coulombs. -2 is +3 coulombs of charge. So there's a total of +3 coulombs of charge in the system. All 3 spheres touch, all 3 spheres separate. How much charge on each one? There still has to be a total charge in the system of +3 coulombs. We divide that +3 coulombs between these 3 objects. There is +1 coulombs of charge on each one of these objects. And imagine how the electrons flow. This one has extra electrons. This one needs them the most, right? This one didn't change. So once we touched all 3 of them together, really all that happened was like, yeah, they might have flowed all around, but in general, there's no net change here, but electrons came out of this sphere into this one. There could have been a slight trade between those two, but once this whole system plays out, there's going to be just +1 coulombs of charge on each one of these systems. But always think, how are the electrons going to want to move in order to balance things out? And also notice, this is still charging by conduction. So all 3 of them not only end up with the same sign charge, they end up with the same value of charge. If these spheres weren't identical, goes a little beyond what you guys need to know right now, but if these 3 spheres weren't identical, maybe there was different sizes, the charge might not flow evenly, but all 3 spheres will still end up with the same sign charge. Okay. Hope everyone's feeling okay. I'm a YouTuber now, so like and subscribe. Wow. All right. I'm going to leave you with another electrostatics puzzle. Aren't these fun? Your goal for today, the assignment for today, is to solve this puzzle. I want you to give me the answer of what's going on here. The diagram below shows the initial charges and positions of 3 metal spheres, R, S, and T. Because why not? R, S, and T. Sphere R initially has 0 elementary charges. Does that mean it has no charge on it whatsoever? No. It just means that if we add up all the positives and negatives, there's a total balance of charge. There's no net charge on that sphere. This one has a net charge of 8 lowercase e. Remember, lowercase e is the elementary charge. It's another way to measure how much charge is here. This, because it's negative 8e, it has literally 8 extra electrons on that sphere. There's no other way for this sphere to be charged by negative 8e. There's exactly negative 8 extra electrons. There's exactly 8 extra electrons on that sphere. This one is plus 6e, so it's exactly missing 6 electrons. Okay. So then going through here, sphere R is brought into contact with sphere S and then removed. And then sphere S is brought into contact with sphere T and removed. What is the charge on sphere T after this procedure is completed? All right, a tricky thing to keep in mind too, you can't have half of elementary charges, but you can have half of Coulomb charges. I want you to figure this out. This will be typed up nice and clear in the assignment that I want you to submit. And that's your goal for today. And that's it for now. Hope everyone's doing well. Hope you're all staying safe and healthy. Feel free to reach out if there's anything I can do for you, physics-wise or otherwise. I'm here for you. Have a good one, everybody.